the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcome.
Hello, my name is Roy Simpson, professor of mathematics at Cosumnes River College in Sacramento, California. This video is about properties of orthogonal projections for linear algebra students. You should have already watched my video on orthogonal decompositions, and we're going to step into some properties of those decompositions and projections specifically. But before we do, let's take a moment to hop back to a theorem we learned about not too long ago and notice something if we allow y to be in our subspace W. So here's theorem 5, a blast from the past here. And in this case, we're saying u sub 1 all the way through u sub p forms a basis which is orthogonal for the subspace W of Rn. And then we said, well, for each vector in W, that vector can be written as a linear combination of those orthogonal basis vectors. Obviously, that is true. We know that. Any vector in a subspace can be written as a linear combination of the basis vectors for that subspace. However, the weights in this case are very important. We proved that the weights of those orthogonal basis vectors are given by this formula right here. And yes, that is the coefficient of the projection of y onto the subspace spanned by the u sub jth basis vector. And as such, taking into account what we have just learned from a recent theorem, this guy right here, well, by that theorem that we just showed, if y is in W, then y is equal to this linear combination, which means that y is equal to the projection of y onto W, which should make sense because y is already in W, so it is its own shadow. And that's what this theorem states right here. If y is in W, which is a span of these orthogonal basis vectors, then y is equal to its own projection onto W because, well, it's in W already. It is its own projection. I was going to prove this and do the slow reveal thing, but we've just verbally proved it. There's really no need for me to go through and do the full proof here. But this will move us a little bit closer to this theorem right here, which is the best approximation theorem. Let W be a subspace of Rn and y be some vector in Rn. Then the projection of y, remember that's the shadow of y onto W, is the closest point in that plane, or that subspace, to the actual vector y, in the sense that the distance between y and that projected shadow is less than the distance between y and any other vector within your subspace, where that vector within your subspace is not the shadowed vector. And rather than doing a proof, which is normally in a textbook, I'm going to go ahead and just show you the visual of it. And this visual actually gives us another theorem as you were looking at it. So here's our vector y. I've highlighted it right here. And we want to know what's the shortest distance between the tip of that vector and that plane that is the span of u1 and u2. Now I'm going to give you some options. We'll play a little game here. Is it this distance? Is it this distance? Is it this distance? Is it this distance? Or is it just this distance right here? Now obviously by the tone of my voice, you can probably tell it's that final distance. So that red vector, the norm of it is actually the shortest distance between the vector y and its shadow in our subspace W. That distance is shorter than the distance between y and any other vector. And that's what I was just drawing, the distance between y and any other vector in that plane. And it just so happens that that distance is actually the norm of the projection of y onto W perp. And while I don't have that as a theorem, that's what we're going to take advantage of right now. Before we get there, I just want to express a concept here. We're beginning to see the use of projections at this point. In application, finding the exact solution of a system is often computationally expensive. However, a more economical solution can often be found by allowing for some error, some wiggle room. This previous theorem tells us when the error gets minimized. If you're one of my students, I might have talked with you guys about this in class, where you basically try to minimize the distance in dimension to your target solution. And that's basically what's happening here. You want to minimize the distance between your current vector and a subspace. And that minimized distance in this instance is going to be the length or the norm or the magnitude of the projection of y onto W perp. So let W be the span of these two vectors, u1 and u2. Find the closest point in W to y. Now visually, remember what we just said. The shortest distance between our vector y and the subspace W is going to be the projection of y onto W perp. And we've actually seen this example before. Here are the same vectors right here, and here was the terrible mathematics that we had to go through. But what's important is this piece right here, the projection of y onto W perp. Let's go ahead and move that over to our current problem. And let's reread, because I just noticed all we're being asked to do is actually find the closest point in W to y. I actually think that this should be relabeled to be find the shortest distance in W to y. So I'm going to relabel that. All right, that being corrected, find the shortest distance to W from y. That would just be the magnitude of this vector. Now again, as I mentioned earlier, my fault for having a terrible problem set up here, but such is life. Let's go ahead and find the magnitude of this vector. Now, normally in like a traditional homework problem out of a traditional textbook where somebody's not making up a problem on the spot, you would not end up with terrible numbers like this. That's just how it happens when you make stuff up on the fly. But that's not the point of this problem. The point of this problem is really to note that the projection of y onto W perp is actually going to be our measuring stick for the shortest distance from y to W. And by the way, that vector, the projection of y onto W perp, is the vector y minus the projection of y onto the subspace W. So the magnitude of that is just the square root of the sum of the squares of these entries. There you go. Now, believe it or not, that's all I had for this video. There's not a lot in here, but still very important topics. A little bit of a note at the end here, the idea of finding the closest point in a subspace to a point outside of that subspace is vital in future material. So this will come into play as we move forward. Anyhow, I hope that this made sense to you. I hope my visuals were not too terrible. I hope you have a great day, and please be a wonderful human being.
It's the system of equations. We must deal with them all at once. Always looking for solutions. Positive outlook overcomes obstacles getting in our way. Cause affects more than we can sometimes see. Things for what they are and work together until you feel at peace. Just listen close. Don't talk too much that isn't cold. Sure, you may really hurt inside. It doesn't justify you to speak too loud and cry.